Hello students, welcome back. Let us resume our discussion on section 1. Previously, we studied the theory of cosets and coset relations. First, we established the left coset relation and the right coset relation like these. The inverse comes to the left or to the right. That was the distinction. Either way, we proved that both were equivalence relations. Both are equivalent relations, and consequently, we can consider the equivalent classes of both, and it turns out the equivalent classes of left coset relation turn out to be of this form, A times H, which we call the left coset. You see, this group operation of A is on the left-hand side of the subgroup H. So it's called the left coset. For the right coset relation, it turns out we have something like this, HA form, and not surprisingly, we call it right coset. A is multiplied to the right of the subgroup H. If G is abelian, then of course there's no distinction. The left coset and the right coset are the same because the multiplication A times H and H times A are the same. In general, however, they do not have to be the same. For non-abelian cases, in order to have the same left coset and right coset, we need something a little bit different. This one here. For any element G from the starting group capital G, G inverse HG is equal to H. That's the condition. And you can easily prove that this condition, G inverse HG is equal to H, can be manipulated into HG is GH. Yes, left and right coset are the same for arbitrary G. A subgroup with such a property is called a normal subgroup, and that is going to be very, very important a couple of weeks later, maybe 3, when we deal with factor groups and things like those. Okay, so much for 1.1. Now let's go to 1.2. And in this example, let's re-establish the residue class using a little bit higher level languages. Let's begin with Z, the set of all integers under the addition, and that's a cyclic group. So any subgroup is also a cyclic group, and it must have a generator, so it must be of MZ form. So when M is negative, then replace M by negative M. So either way, we're going to get some positive integer times Z. The coset structure is as follows: 0 plus MZ, 1 plus MZ, 2 plus MZ, and so on, all the way over to M minus 1 plus MZ. The set of all multiples of M, in other words, set of all integers whose remainder is 0 when divided by M. And then the set of all integers whose remainder is 1 when divided by M. And then the set of all integers whose remainder is 2 when divided by M, and so on. And then we continue all the way over to M minus 1, and that's it, no more, because of the division algorithm. These are the left cosets, but the right cosets are the same as well because Z is abelian, so there's no distinction between one and the other. You can add something to the left or to the right, they're the same. Now, the set of all cosets, they're the same as the set of all equivalence classes under this coset relation, right? And basically, we are talking about the quotient set of this equivalence relation. Then, the elements are of this form, R plus MZ form, which we write as R bar as an abbreviation. Yeah, that's one way to represent an equivalence class. And there's another way. And then we can consider the induced operation. You see, original Z was a group under the addition. So originated from that, we define addition to these cosets accordingly. And then, of course, we have to prove that induced operation is well defined. That's going to be a little bit more difficult story. Excuse me, I take it back. It's not difficult. It's tedious at this moment. To generalize it further will be difficult, but for this one, it's just tedious. And consequently, we end up with a group structure, and that's how you get ZM, the residue class group. And this construction is essentially the same as this construction we considered earlier. The equivalence relation, instead of coset relation, we define directly with congruence modulo M. And then we define the induced operation is indeed well defined. We do not consider multiplication here. That's something we're going to do in ring theory, just addition only. And establish everything. Then we have the additive group ZM. Yes, we ended up with exactly the same thing, but using a little bit high level language, using the cosets. Okay, that was one example, but nothing new, because we already knew how to work with residue classes. We have seen it many times. Just change of viewpoint. Now, next example here is going to be relatively new. Let's begin with Z6 and let H be a subgroup given by these two elements. And then let's find all the coset structure. First, we have to prove that this is actually a subgroup. Can you do that? You have to check 3. First, close under the group operation. 2, the identity. 3, the inverse. 0 plus 0 is 0, 0 plus 3 is 3, and 3 plus 3 is 6, but that's the same as 0 modulo 6, so yes, closed under the addition. The identity 0 is here, and as for the inverse of 0 is 0, the inverse is 3, so yes, yes, and yes. So it's a subgroup. Moreover, you can see that this subgroup is actually isomorphic to Z2. It has the same structure. Okay, now let's go to the coset. 0 plus H, 1 plus H, and 2 plus H. There you go. Those are the cosets. Wait a minute, we checked only the first 3. How about the other 3? Well, we can do that, but it turns out they're all duplicates. You see, 3 plus H, but 3 already belongs to H, and H is closed under all those group operations, so it has to be the same as H. Same as H, same as 0 plus H. And then how about 4 plus H? Well, 4 plus 0 is 1. So back to this. And then 4 plus 4 is 8. 4 plus 3 is 7. And that's same as 1 modulo 6. So same as this. And then 5 plus H, well, same as above actually. 5 plus 0 is 5. And then 5 plus 3 is 8. But that's the same as 2 modulo 6. So yes. Those are duplicates. We have only 3. So if you form the quotient set, we have the set of 3 elements here. First equivalence class, H itself, and then the second equivalence class, coset 1 plus h, and the third equivalence class, coset 2 plus h. There is no more, because these are all duplicates. It turns out that the induced operation yields a group structure here as well, and that's identical to Z3. And you can check manually. I mean, there are only 3 elements, so you can check easily. 0 plus 0 is 0, easy. 0 plus 1 is 1. And 0 plus 2 is 2. 1 plus 1 is 2. The only thing that you may have to work out just a little bit is this one. 2 plus 2 is 4, but the same as 1 modulo this. See this green? So 2 plus 2 is 1, and we ended up with the same group structure as Z3. The textbook has a full group operation table, but it's a bit too tedious. I'm not going to do that. I think this is sufficient. And we can use the following abbreviated notation. Z6 divided by H is Z3. I don't know whether this divided by expression is correct or not, but believe me, there is a relation between one and the other, as a matter of fact. By the way, remember the operational structure inside H is identical to Z2. Remember that? You see 0, 3 and versus 0, 1. 0 plus 0 is 0. 0 plus 3 is 3. And then 3 plus 3 is 6, but that's same as 0 modulo 6. How about this one? 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 1 is 0 modulo 2. So yes, these two are identical or isomorphic. Or you can multiply by 3 to get the isomorphism actually. So if I replace this H by Z2, then we're going to get this kind of abbreviation. Does it make sense? And do you think there's a relation between this computation? 6 divided by 2 is 3. Well, a good question. And does it always work? The answer to that question is yes and yes, but the proof, well, that's a little bit different story. And we're going to do a little bit more next week, and a little bit more next week, and a little bit more the next week, kind of like those. And by the time we do normal groups and factor groups and those kind of things, we're going to be done. Okay, here's another problem. This time, let's take another subgroup, 0, 2, 4. And, well, okay, this problem is left to the students. First, you'll have to prove that this is a subgroup of this. Yeah, you'll have to check those 3. Close under the addition. And then the identity, that's trivial, and the inverse. And if you do it right, you're going to get this. Again, 6 divided by 3 is 2. Previously, 6 divided by 2 is 3, but similar. The detail is left to the students here. Okay, so much for 1.3. And let's consider 1.4 in a separate video. And that'll complete this one for now.